Hi, in this video, we want to take a look at comparing different logistic regression models. All right, so remember when we're talking about logistic regression, we have a binary target, so there's two levels, and we are using an S-shaped curve to model the probability of success or failure based off of our predictor variables. Now, what ends up happening is I'm not actually modeling the probability of success failure. I'm modeling the log odds of success. And that's how we approach. And once I have the log odds of success, it's a simple arithmetic to be able to convert that to probabilities. All right. So for this example, what we're going to do is so this is an example from the textbook. I've modified the code quite a bit to make things a little bit cleaner. Hopefully it's easier to read, easier to understand what's going on. All right, so first thing I'm going to do, I'm going to load my data. Now I noticed that we have names in our data set. So I go ahead and make the row names into the restaurant names. That way it's easier to figure out what's going on, which is good practice. If I have an ID variable, you should use that for your row names, but don't drop that. If you're using a lot of the tidyverse functions, the tidyverse functions will drop your row names. So don't ever drop your ID variables out just because you put it on your row names. Just to give you a heads up on that. All right, so I go ahead and just reorganize my data so that it's a little bit more in a I feel like it's more coherent order. I have the ID column, then I have the target variable column, then I have the predictors. Now, before I made this video, I went through and I kind of explored each of these variables, and I concluded that food's most important than price, service, decor. So what this does, it sets it up so that as I start looking through, I can see, hey, it's easier to spot trends when I order my target variables like this. I think this is a good practice if I have, if I had let's say 1,000 predictor variables. If I order them by the correlation with my target variable, I can kind of see how far down the line in that 1,000 do I want to even remotely consider. I find that's an efficient way to go. But the disadvantage is I'm restructuring my data. I'm reordering the columns, which can cost a lot of time. If it's a small project, I think it's worth it. If it's a larger project, honestly, I'm probably not going to bother doing it. Okay, so then I reorder the rows so you see the reverse here. I order it by the core, service, price, food, then the target variable. That way, it might be easier for me to spot any trends that might be hidden in the data. All right, so I've got a binary target variable and I have numeric predictors. So what I'm going to do, I'm going to make box plots. And I'm going to use the box plots to give me some intuition on whether each predictor variable is informative or not. All right, so every time that my target variable is a 0, here's the box plot of the target variable. Every time my target variable is 1, here is a box plot of the target variable. All right, what I want to see the boxes being very different, vertically very different from each other. If I see the boxes like this, then the predictor variable is not very informative by itself. Now, it might be useful, but it's going to be less useful than one where it's like this. So here, remember that food is the one that I feel is the most informative of the four when they stand alone. And so you can see that the boxes, there's a little bit of overlap between the 75th and the 25th interquartile values, but overall they're very different. If I see the lines cutting into each other, if I see the median lines cutting into each other's boxes, then that tells me that there's less informative value in that predictor variable. So that's food. Let's go down to price. All right, so price, it's because of outliers, it's kind of harder to see, but still, it looks like there's something good going on in there. All right, now I see that there's more overlap between the boxes for service. So this tells me that service is probably going to be less useful than the previous two. And then we get down to the core. All right. Now, something about price is you'll notice that it looks like the values of price are kind of skewed, right? If I thought about this as just being one, if I combine all the data into one box plot, you would see that I've got a bunch of values kind of trailing off and forming a tail. And over here, I see that I have a narrow interquartile, the quartile to median compared to the other median to the quartile. All right, so I suspect I have skewed data. If I have skewed data, I might consider using a square root transform or a log transform. It's price, and so usually dealing with money, log transforms is frequently the way I'm going to want to go. If it was count data, I would be leaning towards a square root transform. All right, so let's look at the scatter plot between our predictor variables, see if we have any collinearity aspects. All right, so something that jumps out at me about price is you'll notice that I've got values and then some big ones popping out over here. So it's all clumped up and then it kind of gets stretched out. So that's signaling to me that I have skewed data for price. So once again, that's making me feel like log transform might be something I want to consider. Here, I see that I've got what looks to be like a linear relationship between food and service. All right, so what this tells me is that if I include food, service is not going to be, it will not add as much to the model as I would be hoping. So I might not want to include service if I have food. I might not want to include food if I have service in the model. Now, I see something of a line between decor and food. Now, price, now it gets kind of hard to see when we have like the more skewed data, but I am thinking maybe there's a relationship between price and service, price and decor. So if I have food and price, then I may not want service, I may not want decor in there. And then service and decor, something of a relationship. So like food and decor, it's not very strong. Service and decor, not a very strong relationship. Oh, and something I have to be mindful about, and I didn't adjust for it in this plot, is that there's overlap on these points. Now, if I want to be able to see the overlap better, what I can do, I can invoke a transparency on the color. I didn't do that just because I'm being lazy, honestly. I could also do like jitter. The textbook author, what he did, he made it so that if it's in the model, it's like a triangle or a circle, and then if it's not, or if it's a success, it's triangle or circle, and if it's failure, it's the opposite one. And then if I have overlap for a value that is like a failure and a success, I can see it. But when they're both failure, both success, I don't see the overlap. All right, so let's build the first model. So I'm just going to go through, and I'm going to make the prediction with basically linear with vanilla predictors. All right, I mean, very natural thing to try. So let's evaluate the first model. All right, so I go ahead and I hit summary. So summary is going to check the hypothesis testing of the coefficient being equal to 0 for each of the predictors. So I look down here, and I can see that the intercept definitely statistically significant, food statistically significant, price. Now service, that's 0.12. Now I'm thinking that might not be the best one to have in there. Now decor, I mean that's statistically not significant. So I'll be thinking about removing a term. So now remember, if I'm going to reduce my model, I would want to like remove one first and then evaluate the model. I don't want to remove two at the same time. And notice that for the output, I'm getting AIC, but there's a lot of stuff that was in the regular linear model that I'm not getting here. And we've got null deviance and residual deviance is coming up. And I don't have an F-test. Why? Because F-test, that comes from the same construction as ANOVA, and my residuals need to be normally distributed with constant variance, and covariance between observations need to be 0. Well, we don't have normal distribution because I have a binary target. So I can't use the f-test. Okay, so I can't use the f-test, but I still wanted to ask, is this an informative model? Is this model more informative than the constant model? So my null hypothesis that I want to test is that the null hypothesis is that the model with just one coefficient, that is constant probability, is equally informative as this model here. So constant probability model compared to this model, I want to check to see, are they equally informative or is there a difference? All right, so what we're going to end up doing, we're going to use a chi-squared test. And how I get at this is I do use the ANOVA function, but I'm not doing the ANOVA test. I'm just using the ANOVA function to call the test I want. So what I do, I say test equals chi-squared, and what it's going to do, R is going to select the right aspects or the right statistics from my logistic regression model and compute everything for me. All right, so when I do that, so food, okay, price, service, and then decor. All right, so remember, terms are added sequentially, first to last. So this is asking me, should I add food to the constant model? Yes, I should. Should I add price to the model with food and a y-intercept? Yes, I should. Should I add service to the food and price model? All right, well, this one, now we're in the range of maybe, maybe not. And should I add decor to the model with food, price, and service? And so here I would say the hypothesis test is saying, no, I should not add decor. Now let's go ahead and plot my first logistic regression model. All right, so something that's going to jump out at you is like, oh my gosh, there's a pattern. When I'm doing regular linear regression, I don't want patterns. But now I have a binary target. Since I have a binary target, all of the times that my target variable is equal to 1 are grouping together. All the times that my target variable is 0 are grouping together. And so how do I interpret this? I don't know. This is problematic because this curve and this curve honestly is always going to be there if I'm doing logistic regression on a significant data set. So this really doesn't tell me anything because, you know, I'm just looking at the difference between the modeled probability and the observation of 0 and 1. Well, 0 and 1 it's a fixed value. And now I have my normal plot. Well, my normal plot of the residuals is coming from really, you know, the vertical value here, but I can see that, you know, that there's something going on. The blues and green, the blues are grouping together, the greens are grouping together, and I see that again in the normal QQ plot. So this really is not informative. Now scale locations, once again, things are grouping up. If I saw this in linear regression, I would panic and have a heart attack that there's a problem. But here I'm not because I know what's going on with my residuals and expect to see this X pattern when you do logistic regression. Now Cook's distance, now this one might be a little bit more informative that these restaurants I might want to take a look at, especially this one right here, since it's so much larger than all the other ones. And we can see that, like here, so green is where it's equal to 0, if I remember correctly. Yeah, green is when it's equal to 0. And I can see that all the ones that are like popping out on Cook's distance are times that they were not in, or they were failures. So here, like these might be cases where, like these guys probably should have been successes, but for some reason they were failures. You might want to look into why. Maybe there's some other variable as to why these failed. Maybe there's like a health inspector variable that we don't have access to. And that health inspector variable is what canceled out these 3 models. I don't know. I'm just making stuff up. But you know, it's the kind of stuff you want to start looking into when you start looking at these actual plots. And here's the standardized Pearson residuals. And I mean, you can see that everything's grouping up exactly the way they were before. So this really isn't telling me anything. Really, the only thing that is useful about these plots is to go through and look at the observations that are getting flagged to double check that you don't have any outliers or anomalies in your data set. Okay, so let's go ahead and let's do some plots. So here, remember that from the hat matrix, that's a way of measuring the influence of a predictor variable. Now the hat matrix does not consider the target variable, it only considers the predictor variables. So when I use that, keep that in the back of your mind. Now here I can get the deviance residuals, and here it's the standardized ones. All right, so remember that deviance is the difference between the observation and the model value. So 0, 1 minus the probability. And now here, Pearson, when I do a Pearson residual, I'm adjusting for non-constant variance. So in linear regression, one of our assumptions is that we have constant variance. In logistic regression, we don't have that. So when I look at my residuals, it is best to look at ones that adjust for the non-constant variance, and Pearson is a good choice for that. All right, so let's look at the standardized deviance by food. And I can see that there's two groups, but I mean, I know what's going on. I know that these are the ones and these are the zeros, so it's not really giving me information. And it's, once again, not really giving me information. Now, at this point here, I would want to take a look at that. This is pretty far off. There's probably something weird going on in my data. Now, that's one aspect that is useful about these plots. I want to start digging in on that one. All right, so I'm not satisfied with this model. And specifically, when I was looking at the predictors, I was thinking, maybe logarithm of price might be useful. So anytime I have a count variable, consider a square root transform. Anytime I have a money variable, consider a log transform. All right, so what I'm going to do, I'm going to basically do the same model as before, but I'm going to add log of price. Now, something should jump out at you about this. If I have price and log of price, then they're going to have perfect Spearman correlation with each other. So, something I want to keep in my mind that I'm probably going to want to remove one of these in a moment. This is how the author proceeded in the example. Honestly, I would have just dropped price and gone with log price at this point. All right, so let's go ahead and let's do a ANOVA test. Now, it's not actually a ANOVA test, it's a chi-squared test. So if I don't specify chi-squared, it's not going to actually run the hypothesis test, but it will give me some statistics that measure what's going on, but it's hard for me as a human being to interpret. It will not give me p-values. If I want p-values, I have to give it a test to run because the default is the f-test, and the f-test doesn't work unless I have normal distribution. Okay, so going sequentially, so terms are added sequentially first to last. Should I add food to the constant model? Yes. Should I add log price? Yes. Should I add price to the food with log price model? Here that's still statistically significant. So yeah, this says I should. Should I add service to the food, log price, and price model? Yeah, it's a good idea. Now, should I add decor to food, log price, price, service model? No, I shouldn't. Now, my personal experience with actual modeling is that it's okay to have one predictor variable that is not statistically significant, but if I have more than one, usually there's going to be a problem in modeling. Okay, so now what I want to do, I want to test to see is the second model equally informative or more informative than the first model. All right, so what I would do previously, I would use a ANOVA test with the F distribution. All right, so here I'm going to use the ANOVA function to do the chi-squared test. So here I'm going to be testing to see, is the second model more informative than the first? My null hypothesis is that they are equally informative. My alternative hypothesis is that the second one is more informative because it has another predictor. If they are equally informative, I want the simpler one, model 1. If model 2 is more informative, I want the more informative one, model 2. So I get my output, and I can see that model 2 is statistically significant for being more informative than the first one. So I want to go with model 2 over model 1. All right, so now let's go ahead and start doing some visualization. So I want to do marginal model plots. All right, so when I see that the non-parametric model that's from my data and the model that I built, if they agree tightly, then I like my model. If I see disagreement, then I want to remove a term. I want to start adjusting. Like I'm not satisfied with it. Okay, so if I go with food and binary target, these match up nicely. If I go with log price and my target, and you can see it's a nice S curve. All right, things are looking good. Now here, there's a little bit of difference. When I plot all these out like this in ones, it's kind of hard to zoom in, but otherwise there's gonna be a lot of plots. But you know, this isn't too bad. What about price and its curve? Well, there's a little bit different over here, but you know, when we start looking at non-parametric estimates on the far left and far right, expect things to not really work the way we want them to. They get kind of wiggly, like a limp noodle. Service, pretty close. Decor, it's not as tight of a fit as we would like. And then overall linear predictor, there's a little bit of a difference here. All right, so what can we do? Well, let's think about adding an interaction term. All right, so let's say I want to add service and decor. So if I go back up here, look at our scatter plot. I'm thinking about adding service and decor, which is one of the scatter plots that's the most cloud-like. Then maybe this might have the information I'm looking for. All right, so we're going to add on service decor, and overshot it. So we add service decor to the model, and then I'm going to run summary to see if the coefficient is equal to 0, hypothesis test. And I go down the list, and so everything is, you know, so like here, price, I might consider removing price out of there. Then after that, maybe service might be the one that I'm looking at. But price would be the first one I'm going to take off. I'm looking to remove based off of this output, because everything else is a rather small p-value. All right, so now let's go ahead and look at our marginal model plots. And so I've got food, log price, price, service, and this is looks very familiar to us because here interaction terms are not included in marginal model plots. So I'm not going to get a heck of a lot of difference. There will be a difference in there because it's included in the generation of the plots, but I'm not seeing a whole heck of a lot of difference here. All right, so let's go ahead and run an ANOVA test on our third model. Should we add things sequentially? Should we add food to the constant model? Yes. Should we add log price to food? Yes. Should we add price to food log price model? Yes. Should we add service to food log price model? Yes. And now decor is like, hey, no. And then I have service decor, but it looks like service and decor together is informative. So I'm going to go ahead and leave service and decor in for the time being. All right, now let's run a chi-square test to see, are these equally informative? So if I compare model 2 to model 1, model 2 is more informative than model 1. And if I look at model 2 and model 3 is more informative. Okay. So now let's build another model. This time I'm going to remove price. Okay, so I'm feeling like the interaction term is useful. So I want to keep that. And so I'm going to keep service and decor. In a previous model, I saw that price wasn't really doing as much good as I was hoping, and I've already got log price in there. And remember, log price and price will have perfect Spearman correlation. Therefore, removing price is probably the best way to go. So let's go ahead and evaluate the model. And now I'm feeling good about all of these predictors at this point. All my p-values are small. Let's look at the difference between model 3 and model 4. All right, so I can see that here I'm concluding that model 3 and model 4 are equally informative. All right, so if I'm doing model 3, model 4, they're equally informative. That means I want the simpler one of the two. Well, model 3 is the same as model 4, except price. That's the difference. So if I look through, food is in both of them, log price is in both, service is in both, decor is in both, and the interaction term is both. Price is in the third model, but not the fourth. So which model would I conclude is the better one? Well, I would conclude the simpler one is the better one. So I'm going to go with model 4. So the one you put first is model 1 in the list. So let's go ahead and look at the marginal model plots. So remember, the interaction terms are going to be removed. That's looking good. Here, there's a little bit of a difference. That's pretty tight. A little bit of deviation, but not a whole heck of a lot. And this is pretty tight overall. All right, so I'm feeling pretty good about this fourth model. This is the one I would launch if I was using this at work. All right, so that's all I've got for you. Take care and goodbye.